friends, now we are in class 2 or second class of Rouths stability criteria and concept of stability. Next question is, the system shown in figure is, this is the figure of the system, and it is, the question is asking about stability and stability, conditional stability, stable for input U1 but unstable for input U2. So there are two inputs given, U1 and U2, and this question has been asked in GATE 2007. So let me define what is stability and what is unstability. So stability means a system is said to be stable if that it fulfills the two conditions. The first condition is, for a bounded input, the output must be bounded, and the second condition is, in the absence of input, the output must tend to 0, whatever be the initial condition. So if a system is satisfying these two criteria, then the system is said to be stable. So what is bounded input? Bounded means some definite input. If we apply some definite input, then the output must be definite, means within some limit. It should not be like infinite. And second condition is, in the absence of any input, the output must tend to 0. Because suppose you are driving a cycle and you are not giving any input. So how we are giving input to the cycle? We are pedaling it, and by means of pedaling we are giving input, we are giving torque to the cycle, so the cycle moves. Suppose we are not pedaling it, and initially the cycle has some speed, suppose it has 10 km/h. So after some time it must stop. The output means, here the output of cycle is, what is input is the input is pedaling and output is the speed of cycle. So the cycle must stop after some time. If it doesn't stop, its speed goes increasing and increasing, then we say that the cycle is an unstable system. So these two criteria must be satisfied by a stable system, otherwise the system will be unstable. So now I think you have understood what is stability and unstability, and what is condition. And there is one more term, marginally stable. Suppose we are not giving any input and the system is moving at a constant speed, or system is oscillating. You can say a system is oscillating with a constant amplitude. Then we say that it is neither, the output is neither decreasing nor increasing, it is remaining the same, and hence the system is marginally stable. Neither it is unstable nor it is stable, it is marginally stable. So now we have, I think you have understood what is stability, unstability and marginal stability. So it all of these depends upon what is the location of roots. What is the location of roots? Roots means what is the location of poles of a transfer function. So what is the location of poles of transfer function? So if all the poles or all the roots of characteristic equation are lying in left half of a plane, then the system will be stable. If all the poles are lying in right half of a plane, then the system will be unstable. And if all the poles are lying in left half, except some poles are lying on imaginary axis, then the system will either be marginally stable or be unstable. That will depend upon whether the poles lying on imaginary axis are repeated or non-repeated or non-repeated. If the poles are non-repeated, then the system will be marginally stable and perform sustained oscillation with constant amplitude. And if the poles are repeated, then the system will be unstable. Okay, so now I think you have got what I am trying to say. Then also let me write what is the stability, what is unstability. So let me write the definitions. So stability, and before writing the definition of stability, let me explain some more thing. We determine the stability of a system in two domains. Either we can determine in time domain or in frequency domain. So the most basic criteria for determining the stability is Rouths stability criteria. This is the most basic criteria for determining the stability of a system. It is also called Rouths service criteria. So this is a time domain approach. Other time domains approach are root locus technique, and the frequency domain approach are Nyquist stability criteria, Bode plot, etc. So either we can determine the stability of a system in time domain or in frequency domain. So but all of these criteria depend upon the location of poles. Location of poles means if the system is a closed loop system, then we determine the location of closed loop pole. If the system is an open loop system, then we determine the location of open loop pole. Okay, so the stability of a system depends upon the location of poles only. So let me write what is stability. A system is said to be stable. A system is said to be stable if number one, for bounded input, we get bounded output. And number two, in the absence of any input, in the absence of any input, the output must tend to 0. Okay, this is the basic criteria of stability. So now let me write location of poles and stability of a system. Location of poles and stability of a system. So before going to location of poles, what is pole? Actually, pole is the roots of characteristic equation. Now, what is characteristic equation? So characteristic equation is if we make the equation from the denominator of a transfer function, then that equation is called characteristic equation, because it determines the character of the response of a system. That's why it is called characteristic equation. Now, what is transfer function? So let me define transfer function. So transfer function. So transfer function is nothing but, it is generally denoted by TS. It is the ratio of Laplace transform of output is to Laplace transform of input, taking all initial condition 0. So what is it? It is the ratio of So it is the ratio of Laplace transform of output is to Laplace transform of input taking all initial conditions zero. So what is initial condition? Just I have given one example. What was that? If a cycle is running with some speed, suppose 10 km per hour, then that is initial condition. If suppose a capacitor is charged initially with some charge, then it is called there is some initial condition that capacitor. If there is some current flowing through inductor, then we say that inductor there is some initial condition in inductor. So these are called initial conditions. Means initially that is not at rest, that is not at zero, it is having some value. So if suppose a system is like that, suppose this is the system or process. Suppose this is TS. Suppose this is TS, or you can say system, and this is output YS, and this is input RS. So transfer function TS will be nothing but YS divided by RS. So YS divided by RS will be transfer function, and this RS, suppose now YS divided by RS, this is called transfer function, and suppose it is of the form, you can say S to the power or you can say S to the power m, or you can say B naught plus B1S plus B2 S square dot plus Bm S to the power m divided by A naught plus A1 S plus A2 S square dot plus An S to the power n. Now let me wipe out, then we will explain other things. Now we can write ds from here as ns by ds. Ns means numerator divided by denominator. So it is B naught plus B1S dot plus Bm S to the power m divided by A naught plus A1S dot plus An S to the power n. Now this ds is nothing but this. Now ds equal to A naught plus A1S dot plus An S to the power n. This ds is called characteristic polynomial. This is called characteristic polynomial. And if we express this polynomial in equation form, that is ds equal to 0, then that equation is called characteristic equation. And ds equal to 0, that is a naught plus a1s plus dot 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 a naught an s to the power n equal to 0 is called characteristic equation. Let me write it by that characteristic equation. And the location of roots of this characteristic equation, that is poles of this transfer function, determines the behavior of response of the system. The location of roots of characteristic equation also called the roots of characteristic equation, also called what it is called, also called poles or eigenvalues, determines the behavior of response of the system. So how it determines? Let me summarize that. So let me wipe out these things and so that I could summarize. So let me wipe out all those things. Before that, I had given the heading location of poles and behavior of system. Now again I will give the same heading, location of poles and behavior of system. So location of poles and behavior of system. Number 1. If all the poles are lying in left half of S plane, then the system will be stable. If all the poles are lying on left half of S plane. What do you mean by left half? So left half is this is called right half. This is called right half. These are right half. These are right half. This is right half. Suppose this is sigma and this is j omega. So this is right half, and this part is called, this part is left half. This part is left half. Left half. Means left to j omega axis is left half and right to j omega axis is right half. So if all the poles are lying in left half, means left to j omega axis of S plane. This is called S plane. This is S plane. Right half. Let me write here right. if all the poles are lying in left half of S plane, then the system will be stable. Then the system will be stable. Second, if all the poles are lying in right half of S plane, then the system will be unstable. If all the poles are lying in right half of S plane, then the system will be unstable. Case 3. If all the poles are lying on left half except some poles are lying on j omega axis, let me write the case. If all the poles are lying on left half of S plane, left half of S plane, left half of S plane, except some poles are lying on imaginary, that is j omega axis, then two cases arises. If the poles are simple means non-repeated on j omega axis, then the system will be marginally stable and the system will perform oscillation with constant amplitude. And if the poles are not simple, that is repeated, then the system will be unstable. So then A, if the poles on j omega axis are simple means non-repeated, then the system will be marginally stable and perform sustained oscillation with constant amplitude. So let me denote this. Suppose let me denote this clearly. Suppose there is a pole here, then there is a pole here also. This is j omega axis, this is sigma axis, that is imaginary. Here the poles are, these poles are simple because there is only one pole here and there is only one pole here. So these poles are simple. We can say these poles are simple. So these poles are simple. Now case B is let me write this side. Case B. If the poles on j omega axis are repeated, not simple. If the case B. If the poles on j omega axis are not simple, that is repeated, then the system will be unstable. So let me show how. Suppose this is j omega axis, this is real axis. Suppose there are two poles here, okay, and there are two poles here also. Then these poles are not simple, repeated poles. Actually, these poles are on j omega axis for clear visibility. I have shown this in left and this in right, so that it could be visible to you people that there are two poles on j omega at the same place on j omega axis. This is not in left half and this is not in right half. Both are at same place on j omega axis. Like that here also both the poles are on j omega axis, and so this is repeated poles. Another example of repeated poles is this one. This one is also repeated pole at origin, so you can say it is on j omega axis also. So this is also repeated pole. So these are the examples of repeated poles. Okay. So in these cases the system will be unstable. So now I think all of you have understood when the system will remain stable and when the system will remain unstable. So let me wipe out this so that we can solve the problem given. Now let us see. Let us take one input and one output, suppressing the other input. So let us suppress the input U2 and taking input U1 alone. So suppressing case 1, let me write as case 1. Suppressing input U2, the system will be how will it look? It will look like this will be sigma, okay, this will be s minus 1 divided by s plus 2. It will be again here sigma. Now it will be 1 by 1 plus s. Now this will be, it will be plus and it will be minus. and here it will be U1 and it will be C1. C2. This point is C2. So it is not required to show this point C2 because we are taking here the input as U1 and output as C1. Okay. Now here it is plus. So now we can see that it is a negative feedback system with C1 as output and U1 as input. So the transfer function of the system will be Ts equal to Gs divided by 1 plus Gs into Hs. Here Gs will be S minus 1 divided by S plus 2 and Hs will be 1 by 1 plus S because it is in feedback loop. So the transfer function will be transfer function will be C1s divided by U1s and we can say this as T1s, transfer function T1s. So T1s will be how much? This is Gs, so Gs divided by 1 plus Gs into Hs. So here S minus 1 divided by S plus 2 into 1 by 1 plus S. Okay. Now we have to add these. So if we will add, then it will come S minus 1 divided by S plus 2 divided by here S plus 1 into S plus 2. Okay. And here S plus 1 into S plus 2 plus S minus 1. Okay. Now it will be S minus 1. S plus 2 will cancel out each other. So it will be S minus 1 multiplied by this S plus 1 will go in numerator divided by S square, here S square plus 3S, okay, plus 2 plus S minus 1. Now it will be S minus 1 into S plus 1 divided by S square plus 3S plus 1. Okay, so it will be S minus 1 into S plus 1 divided by S square plus 3S plus 1. So here it is S plus 1, so S plus 1 will go in numerator, so it will be S square minus 1 and S square minus 1, okay, divided by S square plus 3S plus 1. Now the characteristic equation is this one. Denominator is the characteristic equation. Now the characteristic equation is S square plus 3S plus 1 equal to 0. If we find out the roots of this characteristic equation, then S will be nothing but minus 3 plus minus under root B square. B square means 9 minus 4AC divided by 2. So it will be minus 3 plus minus under root 5 by 2. Since under root 5 is less than minus 3, so if we, whether we add with root 5 or subtract with root 5, the roots will always be negative. So both the roots are lying in left half of S plane. So both the roots are negative, and so the system will stable for input U2 because let me write here. Here both the roots are, or let me write on that side, let me write on that side. Since both the roots are negative, both the roots are negative, the system will be stable for input u1. Okay, so now the system is stable for input u1. Now let me check the same for input u2. So let me write out these things so that we could check this for input u2. So it will be case 2. So now case 2, suppressing input u1. So now we have to suppress input u1. So we have to suppress input u1, and now we have to take input u2 only. Okay, so if we take input u2, this will be C2, and this is 1 plus s. Okay, this is 1 plus s. Now it is here, it is now this is sigma, and here it is like it is plus, again it is plus. This is u2, this is again plus, so it is again plus, it is plus, so now this is C2. Now the transfer function will be C2s divided by u2s, and now gs will be this one, 1 by 1 plus s, and hs will be this term, because this is in feedback path, and here also this will be negative feedback because it becomes negative here at this point. So now the transfer function in this case will be, so the transfer function will be how much? T2s equal to C2s divided by U2s, and this will be equal to nothing but gs. Here gs is 1 by 1 plus s, gs divided by 1 plus gs into hs. So 1 plus this is gs into this is hs. Now how much we will get? So now we will get s plus 1 into s plus 2 plus s minus 1, okay, plus s minus 1 multiplied by here s plus 2 will s plus 2 into s plus 1 will go in numerator, and here s plus 1 plus s will come in denominator. So here we can write s plus 1. Okay, so this s plus 1 will cancel out this s plus 1. So now s plus 2 divided by the same thing as it was earlier. Here also s square plus 3s plus 1. So here also we can see the denominator is same, means the characteristic equation is same, and hence the characteristic roots are same. Here also the characteristic roots are same, and that they are lying in left half of S plane, and hence the system is again stable for the input U2. So here again the characteristic roots are same and hence same as previous as case 1, and hence the system will be a stable for input u1 also. Hence we can say that the system is always stable, whether it is for input u1 or input u2, and hence in conclusion is that the system will be stable. So which one of the four given options is correct? So option number A is correct, because the system is always stable. It is neither unstable nor conditionally stable, and the D option will also be not correct, because it is stable for u1 and unstable for u2. So option number A is the correct one. Now at the last of the lecture, I would like to share one of the most important thing to you people, that if you like my video, then you must subscribe my video, so that there is no need to search out new video. Automatic update will come if I upload the new videos. What you have to do, it is very simple. There is a circular logo coming in right of me. You have to just click on that to subscribe.